Hello everybody, we move forward with our introduction to Green's functions. Okay, and today we're going to discuss one of my favorite topics, which is material response and causality. Okay, material response and causality. This, of course, in the context of Green's functions, which is what we're actually discussing throughout these days. So let's just underline the title of the lecture and let's start. Okay, so to just put things into context, let's consider the following example. Let's say we have a 3D material. So we have a layer of material here, see? And then let's make it 3D just for small generalization here. So I'm not very good at drawing stuff. So then let's say that this is just a piece of material, and let's say that I shine light on this material. See? So this is a light field. Of course, you can recall that the power of this field, S of t, is proportional to the cross product between the electric field and the magnetic field. But then we're just going to say that the power or the intensity of this field is just represented by some arbitrary function f of t. Okay, so but just recall that this let's say this light field, this optical field, it has to do with the electric field and the magnetic field in this form. This is the Poynting power. And then once you shine light on it, let's consider or let's assume that then you can measure just some current that is generated as a response to the light field. See? And of course, since this light field is local, then the current you're going to measure at that point, it will be local as well, though there will be some spread of the electrons and stuff like that. So it depends on where you put the probe and stuff like that. But in the more general case, let's say that this current here is local, J of t, and then I can say that J of t is the response to an excitation, or F of t, which is the optical field. So this is the excitation. Okay. Nonetheless, you can extend, let's say, this picture into non-local fields, which means that if you have a layer of material as such, so like this is a bit less worse than the other one, I guess. And then let's say that you just shine light globally on the sample. So this is the sample of material, and then you shine light here, you shine light here, you shine light in several places. See? And then that means that now this light field, so your excitation can be written as a light field F of RT. See? So then that means that you will have different intensities of light depending on the coordinate at which you're shining light on. So then that's one thing. And then the current. So then what will happen to the current? Depending on where you put the probe. If you put the probe here, between here and just let's say some neutral point in the material, so the current going through there is going to be J of R T, where R is just the point where you put the probe, because you can this probe here, you can just put it anywhere you like. So let's say you put the probe here, so then that means if you put the probe there, there will be a different coordinate R. So then the coordinate, the actual place where you will put the current probe will be just given by the coordinate r. Okay, so then that leaves us with some response J of RT that now is global. It's not only local, but it's global as well, which depends on the coordinate R. Okay. Now, what other let's say example of excitation and response can we come up with? So let's say, or let's assume that we have a material with some random domains, some random magnetic domains. Let's say this is a 2D material, just for simplicity, and it has some atomic domains that are randomly oriented. Okay. What does that mean? That means that if they're randomly oriented, that means that if I want to measure the magnetization of the material, M of R comma T will be equal to 0. No magnetization, no magnetism in the sample. This is for B, for a magnetic field, of course, equal to 0. Now, what happens if I just turn on a magnetic field and I apply it globally? See? So that means that I apply a magnetic field here, 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 uniformly across all the sample. Yeah? So then, this will be some magnetic field, B of R comma T, that will be different than 0. And then the atomic moments will align, or will tend to align, with the magnetic field. That depends on some other stuff there in the material, but in general they will have the intention to align with B, and then that means that when we measure the magnetization of the material, it will be different than 0. Okay, so then in this case, what do we have as excitation and response? So then we can say that we have this as an excitation, so magnetic field B of R comma T different than 0 plays the role of the excitation. Okay, and we can say that the measure magnetization which is M of R comma T different than 0 is the response. The last example that I can give you is, for instance, when you polarize with an electric field a material. So then let's say that you apply an electric field to a material using just a voltage source that produces an electric field. So we know that. And then so we will have an electric field, an electric field E of R comma T will create a polarization. P of R comma T in a material. What that means is that we have here, let's use green now, we have some excitation that will be the electric field E of R comma T, and we have a response which will be the polarization P of R comma T. Okay, so this is more or less the picture that we have, just in case you wonder. When we talk about polarization in matter, polarization means that if you put an arbitrary particle, charged particle in the material, the motion of that particle will be affected by the polarization of the material. So it means that the polarization of the material is the tendency of charged particles to move in a given direction. That's what polarization means, okay? So then, but we're not talking about electrodynamics in this very video. We're talking about Green's function. So then let's move forward to the formality. Now that we have, let's say, some, I have tried to provide a bit of clarity about what's the context in which we develop response theory in materials and stuff. So then let's talk about the formality. So usually in the dynamics of a system is determined by the impulsive response of a system. So that means that the excitation determines the response once the main characteristic of the system is known. And in that way, then we can write the response of the system, y of t, an arbitrary response of an arbitrary system, as a convolution integral from -infinity to +infinity of some arbitrary kernel g of t comma t prime times some excitation evaluated at t prime, and we integrate over dt prime. So this is what is called the convolution integral. Convolution integral. And this convolution integral is the let's say the main way in which a system can be represented. What is everything in this integral? So then y of t is the response. X of t is the excitation. And g of t comma t prime, which is an important object here because g of t prime contains all the dynamics and all the information about the steady state of the system. Then therefore, once this g of t comma t prime is known, once the excitation x of t prime is provided, then we can know, or we can completely determine the response. So this g of t comma t prime is what characterizes the system. That's the very bit of information that we're looking for in actually to determine any response to an arbitrary excitation x of t. And this is usually called the impulse response. And in more general terms, or let's say in what is mainly known as in the language of physics, and what we're developing in this course is known as the Green's function. Okay. So the Green's function, let's write it down. The Green's function contains all information about the dynamics and steady state behavior of an arbitrary dynamical system. Okay, this is how we should understand the Green's function in terms of system dynamics. And there is one important thing to highlight here, which is this. Once we have determined the Green's function, in a linear system, this is very important, but I'm going to say in a linear system, all the physics can be determined once we have provided the excitation. If the excitation is an electric field, if the excitation is a magnetic field, if the excitation is a combination of both of them, like in the optical field, if the excitation is mechanical stress, once we know the Green's function, all the physics of the system can be determined. So then this has to be very clear. So Green's function, very important object. Green's function, or impulsive response, is a very important object. Okay, so then now we're going to proceed with this. So let's try to from the general formula for this is what's called the convolution integral. From this general convolution integral, let's particularize the convolution integral for LTI systems, which is linear time invariant systems. Okay, when a system is linear and time invariant, so the Green's function d of t comma t prime becomes a function of the difference between the two times. That's what basically, that's the consequence of linearity and time invariance. So of course we already assume linearity, so then and it's not a big assumption, because the systems that we treat with the Green's function, they are usually linear, and when the system is nonlinear, then of course we're gonna use the Green's function as it has been derived, so we have to use something else. Then under this assumption, I can write the convolution integral y of t equal to minus infinity to plus infinity g of t minus t prime x of t prime dt prime. What happens when the excitation has the following form? If the excitation is equal to a delta of t minus t0. So just basically, if I plot the excitation, I will get, let's say this is here, this is t0, and my excitation is just a small impulse around t0. This is x of t, this is t. Okay, then what happens then? So what will happen then is that then y of t is equal to the integral from minus infinity to plus infinity of g of t minus t prime times delta of t prime minus t0 dt prime, and this is nothing but just replace in this function by the properties of the integrals of delta functions, just make t prime equal to t0. So then this is just the integral of this is just g of t minus t0. In this case, we can see something, that when the excitation is an impulse, like here, the response is the same Green's function. That's why the Green's function is called the impulse response. Okay? So then, now that we have said this, let's just move forward a little bit, and let's consider what happens in the spectral domain. So then, when we have a convolution integral of a linear time invariant system, then let's write it again. We have a quite interesting property that it can be used to move between two domains, time domain and Fourier domain. So then this integral, when you Fourier transform y, what you're going to get is that in the Fourier domain, y hat of omega, just to more or less just to establish that the two functions are different in the time and the omega domain. It will be equal to g of omega times x of omega. Okay, so then this what we have here is that it's a property that says that a convolution in the time domain transforms as a product in the Fourier domain. That's what that means. Okay, so then this is a very nice identity, very nice property, and then this property is dual. That means that the product in the time domain. So if let's just use a different representation. So if I have some function a of t, which is equal to some function h of t times b of t, in the spectral domain or in the Fourier domain, this will be a of omega. It will be equal to 1 over 2 pi integral from minus infinity to plus infinity of h of omega minus omega prime times b of omega prime the omega prime. So then this property is dual. So we can apply that property both in the spectral domain or in the time domain. And what it says is that if you have a product in one domain, then in the other domain is the convolution. So then this is quite useful property, and we're going to use this property quite a bit in the next few lessons with respect to what we're developing about causality. And now it's time to after introducing the concepts of response theory, very basic concepts, we're going to talk about causality. So then for that, we're going to consider that systems that are represented using the convolution integral given for the response y of t with the spectral representation written here, then can be graphically illustrated like this. You have an excitation on a dynamical system which gives a response. The excitation is x of t, the response is y of t, and the system is characterized by just a function that we know now is the Fourier transform of the impulse response, which is just g of omega. Okay, so then this is our dynamical system, the dynamical system in question. And this, of course, can be a wave. This can be diffusion. This can be a mass in a spring and a damper. I mean, this can be millions of stuff. Physically, this has a very important property. Systems in nature have a property that is known as causality. So dynamical systems are causal. Now, what does that mean? What that means is that for any time t0 at which the system is excited or driven, the response y of t obeys dot dot. What does the response y of t obeys? It obeys this relation that y of t is equal to 0 for all t's less than t0. This is what causality what the causality property says, and we have to impose that property on this dynamical system that we have been studying, on this arbitrary dynamical system. That has to be imposed. So when we construct the Green's function for that system g of omega, we have to make sure that the Green's function corresponds to a causal dynamics, which what this, in other words, this means that the system cannot respond before its drive or excitation is applied. This is actually something that's quite logical, but nonetheless, it's something that has to be developed furthermore, has to be understood, and has to be applying the construction of the impulse response of the system. And then I will just now start deriving some restrictions that we have to impose on the Green's function for the system to be causal, for the dynamics of the system to be causal. So first, since the response, since we're talking about a causal response, in this case, so y of t will be only different than 0 for all t's that are greater than or equal to t0, okay? In the case that t is equal to t0, that means that the system responds immediately after it is excited. That's impossible, experimentally impossible, but it's not theoretically impossible, okay? So then you just have to make some parameter small enough, which is called the delay time, in such a way that once the system is excited, it responds. So then, and these type of systems are not realizable, are not physically realizable, because the delay time is 0 in this system. That's impossible. So then, but of course, in theory, you can do whatever you want, as long as it obeys causality, of course. So then, what this relation implies mathematically, I can write this saying that y of t is equal to theta, which is the Heave psi function of t minus t0 times y of t. That means that this y of t will be 0 for all times less than t0, okay? So then, and this implies as well on the Green's function that, so on the Green's function, of course, g of t minus t prime is equal to theta of t minus t prime minus t0 times g of t minus t prime. And if we just take t prime to be equal to 0, then we just say that g of t is equal to theta of t minus t0 times g of t. Okay, and in the spectral domain, so this reads as a convolution. So then we just say that g of omega is equal to theta of omega convolution with g of omega. And this restriction that we have here is what later will give rise to Kramer's and Kronig relations. Relations that are a direct consequence of the imposition of causality on the dynamics of the system under study. So then that's what the Kramer's and Kronig relations are. Now that we have more or less detailed what we have to do here, so then we're going to continue with the following. So then to impose causality, what we have to more or less agree on is that the Green's function g of t written in the spectral domain, which is just the integral from minus infinity to infinity of the omega divided by 2 pi g of omega plus e to the minus I omega t. This is 0 for all t's less than 0, or less than t0 if we take t0 to 0. So let's just keep the convention we had, which is less than 0. Okay, so then, since the system is time invariant, so it doesn't matter what is your time, where do you put your time axis. So then we can just translate our time axis and just say that t0 is equal to 0 with no problem. So now here there's one thing. Okay, I have been using small g for the Green's function, and this omega plus here. What is this omega plus? This omega plus is a new variable that comes from the following transformation. On the Green's function, I can make this transformation. I can go from omega to omega plus, which is equal to omega plus I omega prime. See? And then this transformation is called as analytical continuation. And this transformation, it will become clear later that this transformation is an obligation to impose causality on the dynamics of the system, which is represented by the Green's function. Okay, so then that's an obligation, this transformation, and when we apply the transformation to the full Green's function g, so Green's function equal to the integral from minus infinity to plus infinity of d omega divided by 2 pi g of omega plus e to the minus I omega t transforms to g of t equal to the integral from minus infinity to infinity of d omega plus divided by 2 pi g of omega plus e to the minus I omega plus t. Okay, and now graphically, what does actually that mean? So then this is what that means graphically. Forgive my drawing skills, they're just awful. Not even terrible, awful. So then this is real of omega. This is imaginary of omega. And originally, before the analytical continuation transformation, let me write the name here, analytical continuation transformation. Before that, omega or the Green's function g of omega had all the poles on the real axis. So the poles of the Green's function were just on the real axis, wherever you want to put the poles. See? Now, then what happens here is that when you perform the transformation, now the poles, they acquire a small, it can be small or not small, well, that depends on where you put the poles. So, but your new variable has imaginary part, which is omega prime. Because remember that transformation is omega plus equal to omega plus I omega prime. Okay, so then this omega prime allows these poles to be moved away from the imaginary axis. You can move them move away from the real axis. You can move them above or you can move them below. See? That depends on the sign of omega prime. So omega prime determines if the poles of G of omega plus lie on the upper or lower complex plane. Okay, this is very important, and then we have to focus on now. After the we will try to evaluate this thing here, and then we're going to see why this comes in handy in this analytical continuation transformation. So basically, the importance of the transformation is the following. So if I write g of t equal to this minus the integral from minus infinity to infinity of d omega divided by 2 pi of g of omega plus e to the minus I omega plus t, and then we replace here omega plus equal to omega plus I omega prime, then we end up in, sorry, this is omega plus here as well, and an integral of this form, d omega plus divided by 2 pi. So g of omega plus e to the minus I omega plus I omega prime times t. Okay, so then what is this equal to? So this exponential, let's check that this exponential is just e to the minus I omega t times e to the omega prime t. Okay, this factor can be pulled outside the integral. So then this integral is now e to the omega prime t, the integral from minus infinity to plus infinity from d omega plus of the omega plus divided by 2 pi g of omega plus e to the minus I omega t. Okay, if we just check this properly, now we can see that this is originally what we had to calculate. This is because the differential of omega plus, well, that doesn't make a big difference here. So then by calculating, in order to calculate something like this, it will be, the trick is that it's easier to start with something like this. That's the trick. So the trick is that when this thing here, this integral that I just have highlighted here, contains the actual Fourier transform that we started with, which is the integral from minus infinity to plus infinity of d omega divided by 2 pi g of omega e to the minus I omega t. That's contained here. But this is a really hard integral to do. It's hard integral to do, and it probably will not converge, because when we have complex integrals, it depends on how you calculate the integral. I mean, the value of the integral depends on how you choose to evaluate the integral. This is what I'm going to show you. I know this is not the most interesting part of the lecture, but we have to do this. We cannot waive this part. So then, the thing is that when you have the integral in this form, it's much easier to calculate, and once that's calculated, then you can just know what this is. So then, as a matter of fact, so what I'm going to do is that I'm going to say that the integral from minus infinity to plus infinity of d omega plus divided by 2 pi of g omega plus e to the minus I omega plus t is nothing but this factor e to the omega prime t times the integral from minus infinity to plus infinity of d omega plus divided by 2 pi g omega plus e to the minus I omega t. Okay, so then now this is the messy part here, so just pay attention. Remember that we're going to impose that g of t is 0 for all t's less than 0. And then that means that when t is less than 0, when t is less than 0, what we better have is that this factor here tends to 0. That's what we better have, okay? So then that means, how is that going to be 0? So then if omega prime tends to infinity and t is less than 0, that means that omega prime t tends to minus infinity, which means that e to the omega prime t tends to 0. So this is the first thing. For t less than 0, omega prime is positive. It's positive and large, okay? So then that means that we have to choose. We have to choose a way in which this integral here is calculated in such a way that in the complex plane, the omega pluses have positive imaginary part. This is what we have to impose. And if we impose that, then that factor there is going to be 0. Now, for when t is greater than 0, for this factor there to be 0, then omega prime has to tend to minus infinity. Okay, this gives us an idea of what we have to use to calculate that integral. And then we're going to now introduce contour integrals. It's misspelled this, sorry. Contour integrals. In the complex plane. And then, this is this. If I have a time integral in the complex plane like the one we have here, that's why we introduce this omega plus to force that integral to be evaluated in the complex plane. So because the poles of G will be complex. So then when I have this type of integral, that integral is hard to just evaluate like that. You have to choose a path in the complex plane in which you want to evaluate that integral. So then if you have the complex plane here, so for instance you can choose a path like this, see, and then in this path you calculate what just the integral over that closed path is if you of just some function f of z dz. What is this? See, so then and of course we know that what we have is the integral of d omega plus divided by 2 pi g of omega plus e to the minus I omega plus t. See, so then what we want to do is to check what is the best contour, closed contour in which we can evaluate this integral. See, and then for that we're going to use the facts that we just say here, that omega prime has to be positive for t less than 0, and at that point that integral has to be 0 to impose causality. Okay, now in this case we're going to recall that about the Cauchy theorem for complex integrals. So the integral on a closed path of just a function f of z dz is equal to 0, and the closed path is contour c. This is equal to 0 if contour c encloses no poles of f of z. So if there are no poles inside the contour C, so let's say that this contour is C here, and if we have no poles of the function we're integrating over that contour, then the integral is 0, okay? Now what happens when we have poles? So if we have poles, then the integral on that contour C of f of z dz is equal to 2 pi I, the summation of all the residues of the function f of z. That's what we're going to use to evaluate things. We're going to broadly use this theorem. And then we have to choose then a contour in such a way that omega prime is positive and tends to infinity. This is important now. So then for that purpose, I'm going to draw here, at least I'm going to try to draw a contour in the plane omega in such a way that we have imaginary part of omega plus, real part of omega plus, and then we're going to evaluate the integral that is of interest to us in this contour. We're going to draw a contour like this. See? And then this contour is going to be called C plus. C plus. And then this contour is going to be the semicircle, we're going to call it C plus omega, and the line we're going to call it C plus L. That means that the contour C plus is equal to the contour C plus omega plus the contour C plus L, where omega is the radius of the semicircle and it tends to infinity. Okay, this is important because if the semicircle will enclose any given pole, then the poles can have infinite imaginary part, and this is something that we're looking for. So then now, since we're integrating from real omega, so the omega is the line, the real axis, from minus infinity to infinity, we as well, since this is a semicircle, so if this distance here is infinity, so this distance here is infinity as well. That's why we need a semicircle, because we are integrating from minus infinity here to plus infinity here in the real omega. Now the omega prime is just the analytical continuation variable that we have to choose, that it will be large enough. So that variable has to be large enough, okay? Now, this is for t less than 0, because we choose omega prime to be positive, that's in large. And for this integral that we're calculating over this contour, this integral over that contour, I draw it like that, the omega plus divided by 2 pi equal to g of omega plus e to the minus I omega plus t. This is the integral that we're going to evaluate on that contour, so this integral has to be evaluated on C plus. And then, since C plus is the sum of these two contours, so then this integral is equal to the sum of two integrals over each of these contours. So then this is equal to the sum over this contour, which is C plus omega, with limit for omega tending to infinity. This is d omega plus divided by 2 pi g of omega plus e to the minus I omega plus t. And then, since this line here is just infinitesimally, we have chosen this line to be infinitesimally above the real axis. That means that the contour C plus L goes from the point minus infinity, comma, eta 2 plus infinity, comma, eta, where eta is infinitesimal. So that means that the integral in this contour or trajectory, that is just a straight line, which we denoted as c plus L, that integral here makes omega to only have real part, because eta is just infinitesimal there. So the value of eta is constant and is very small, okay? So what we can do is that we just ignore omega prime in that contour, in the line, and we write d omega divided by 2 pi g of omega e to the minus I omega t. And this here is nothing but the Green's function. So this is g of t. And in that case, so we will see that then this is equal to then g of t plus this integral that we have here, and that we know that that integral is plus e to the omega prime t integral on that contour of the omega plus divided by 2 pi g of omega, and e to the g of omega plus e to the minus I omega t, okay? And this, we know this part here, we know is 0 because this factor tends to 0 under the given condition, so this is just equal to g of t. Okay, so that means that g of t is equal to the integral over this closed contour here of the omega plus divided by 2 pi g of omega plus e to the minus I omega plus t over c plus. And this has to be imposed that is equal to 0 for all t less than 0. Then, now that we have derived this condition, that is this integral, the one that has to be 0, then we have to ask ourselves, how is that integral 0? So then from the Cauchy theorem, we know that an integral over a closed contour C of some complex function f of z dz is 0 when C encloses no poles from f of z. From this, then we derive the causality condition, which says that causality condition g of omega plus encloses, or let me write it this way, g of omega plus has no poles poles, yeah, because the poles of E will be that this term here, yeah, that will be this term. So g of omega plus, what are the poles of the exponential function? So the poles of the exponential function will lie on of that exponential function. Yeah, they will probably lie on the imaginary, in the negative imaginary, yes. So then that means that the causality condition says that this g of omega has no poles on the upper complex plane, which guarantees that g of t equal to the integral over c plus of d omega plus divided by 2 pi g of omega plus e to the minus I omega plus t is equal to 0 for all t less than 0. Okay, so then that's guaranteed when g of omega plus has no poles on the upper contour. Which means, which leaves us a very important condition. For causality to be guaranteed, all the poles of this Green's function here, all the poles for g of omega plus have to lie on the lower complex plane. This is the condition for constructing G of omega. So we use this causality condition to derive G of omega, which determines the dynamic and steady state behavior of our system. This is quite important, and then that's how causality relates to Green's functions, and causality imposes that restriction of the Green's function. And then so next video I'm going to do an example with the Lorentz oscillator. Let's just announce it here. Next example using the Lorentz oscillator. So just keep tuned with this, and then next tutorial will be much more applied than this one, but this was important to derive the notion of causality and the relation of the Green's function. I think this is very important. This actually took me a long while to learn when I started in this business, so I just wanted to share this with you. Hope that you try to enjoy this maybe very cumbersome mathematical concept of analytical continuation, contour integration, and then we will see in the next video. Thanks. Bye.